Hi everyone. This is going to be a relatively short recording, I think, unless I have more things to say than I think I do. Let me plug in and this is, if you don't want to listen to this, that's okay. I won't get my feelings hurt, but it's interesting. So what I want to talk about is the material, in section, I think it's 9.4 on method. It's a systematic trees. I want to talk about this because it's interesting. I won't put it on the quiz, but it's interesting. It has to do with what we observed about infinite trees a couple recordings ago. So we've seen that some finite sets of sentences of PL do not have finite truth trees. So it turns out that there's no mechanical test, no procedure that's always going to give an answer after a finite number of steps, right? So the issue is this. Let me write it down. We've seen that some finite sets of sentences of PL do not have finite trees. They may have a branch that goes on infinitely. So we saw an example of this, and the example that we saw was this. The sole set member was for all x, there exists a y, Lxy. And when we do the tree for that sentence in accordance with our tree method, we first apply universal decomposition, and we get that. Then we apply existential decomposition. We have to choose a new name, so we get that. And now, since we've introduced a new constant, we need to go back and instantiate for x again in line number 1, and we get there exists a y, Lby, and we get that from 1 by, whoops, that's not a set member, I'm sorry, I wrote down the wrong thing there. We get that from 1 by universal decomposition, and we get this from 1 by universal decomposition, and now we have to apply existential decomposition to line number 4, and we get LBC, and we get that from 4 by existential decomposition. We've introduced a new name here. We have to go back and apply universal decomposition again, and so on. So this tree is never completed, right? This tree is never completed. It has an infinite branch. Okay, well, we can't do anything about the fact that some finite sets have infinite trees. That's just the way it is. But there are two problems with our tree method that we can resolve. One of those problems is not all that interesting, but I'll mention it really briefly. So the first issue is that we would really like to have a method that produces a finite tree when a finite tree exists, right? So if a finite tree exists, we want our method to produce it. So for instance, we've adopted informally a strategy for how to deal with a tree such as this, right? Namely, the strategy is that we recognize that there's really no reason. I'm putting the same tree down over on the right hand side. There's no reason when you decompose. So suppose over here we're going to decompose line number 1, and we get FA, and we get that from 1 by universal decomposition. And informally, we adopted the strategy of not introducing a new constant if we didn't need to. So we would get not FA from 2 by universal decomposition, and it closes. But that was an informal strategy that we adopted. We could make that more formal, and this is one of the problems that the book discusses in this section, which is, again, it's not very interesting, but I'll mention it. Because, if you were kind of dopey about it, you could say, Okay, so I get FA from line number 1, and oh, I can get FB from line number 1. Oh, I can get FC from line number 1, and so on. And so this tree could go on infinitely, but it doesn't have to, because obviously it's going to close. It's going to be there's a finite tree, in fact, a closed tree, if you think about the your instantiating constants. So the book gives some rules for ordering the decomposition, which we essentially have adopted informally anyway. Okay, but the more interesting issue has to do with a tree such as this. The more interesting issue is that we would really like to have every finite set of sentences that does have, that can be verified in on an interpretation with a finite universe of discourse. We would like the tree to give us those finite, those interpretations with finite universes of discourse, if they exist. And I'm hesitating the way I'm speaking because I want to introduce a new word, and the word is model. And what I mean by a model is just an interpretation that makes the set members true. So when I talk about a finite model, what I mean is an interpretation that makes a set members true that has a finite universe of discourse. Okay, so if we go back to the sentence that I've got up here, let me write it down here. For all x, there exists a y, LXY. Well, we saw that if we do the standard, if we apply the standard tree method to that sentence, it's going to go on infinitely. And what it is suggesting is a model with an infinite universe of discourse, an infinite model. So it would be something like, it would look like that and go on infinitely, right? So we would have A bears L to B, B bears it to C bears it to D, and so on. And so what that suggests is an infinite model. But we've also saw that this sentence has many finite models. So for instance, if you have just one thing, is this pen going to run out again? If you have one thing and it bears L to itself, then this sentence is true in that world. So that would be the finite model would have its universe of discourse, one thing, and into the extension of L, we put 1, 1. So we have one thing that bears L to itself, and it turns out that everything, of course, everything in the universe bears L to at least one thing, namely itself. So, and there are, ever so many more finite, in fact, there are an infinite number of finite models, right? You could have two things, and they bear L to each other, or they bear L to themselves. I don't know what's going on with this pen. Or they bear L to themselves. So you could have a universe of discourse that has two things in it, and into L you could put, 1 bears it to 2, and 2 bears it to 1. That's another finite model of this for this sentence. But our tree method won't provide those models. And what I mean by a tree providing the models is that when you collect the literals from the branch, you get that interpretation. The only interpretation that you're going to get, or is going to be suggested by the traditional tree method, is going to be an infinite model. It's going to be a universe of discourse with an infinite universe of discourse. Okay, so the book gives a really interesting solution to this problem, and the way in which they treat it is by modifying the existential decomposition rule, right? So they modify the ED rule. I'm going to call it ED, okay? So before I talk about what that modification is, let's first remember the reason that we have this restriction on the existential decomposition rule. So this was a question on the last quiz. So I know that you guys have thought about this. You know, if you have the two sentences, there exists an X, there exists an F, and there exists something that's not F. My pen seems to be acting up. If you were to ignore the restriction on existential decomposition, this tree would close, but it shouldn't close, right? But if you do it paying attention to the restriction on existential decomposition, you're going to end, what it's going to suggest is an interpretation that has two things in the universe of discourse. I should have checked those. One from existential decomposition, and then we have not FB from two from existential decomposition. And so this gives you the interpretation. It's got two things in it, and one of them's in F, so it'll be two things in it, and we're going to put one of them into F and leave the other one out. Okay. So yeah, that was our reason for having the restriction on existential decomposition. However, there are times when ignoring the restriction on existential decomposition does not get us into trouble. So for instance, if we have this set, the set that has, there's something that's F and there's something that's G, and so if we were to do that, that tree in the traditional way, we'd end up with we'd end up with that tree, which suggests an interpretation that's got two things in it, and we put one of them into F and we put the other one into G. But look, this could be true, these two sentences could be true in a one-membered universe of discourse, right? So think about this. If we ignored the restriction on existential decomposition, let's do the tree again. So we apply existential decomposition to line number 1, and we have that. And now I'm going to ignore the restriction on existential decomposition here when I decompose line number 2, and that's fine. So what we get from this the wrong tree, so to speak, we end up with a universe of discourse that's got just one thing in it, and we put it into both F and G. Well, that's okay, because that interpretation is one where there's something that's F and there's something that's G, and it happens to be the same thing. We violated the restriction on existential decomposition here, but it actually, that violation led us to another model for that set of sentences. So what we're going to do when we modify the existential decomposition rule is we're going to capitalize on this observation that sometimes it does get you into trouble, and violating the restriction sometimes gets you into trouble, and other times it does not get you into trouble. Okay, so here is the new rule. So what I'm going to do first is I'm going to give you the rule in the way it's stated in the book, and then we're going to look at some examples, and then we're going to see how introducing this new rule to the tree method will solve the problem we were just talking about, that it will enable us to retrieve finite models for sentences when or sets of sentences when finite models exist. So the new rule is this. It's called existential decomposition 2, ED2. And what it tells, it's a branching rule. And what it tells us is that if we've got an existential decomposition, it branches, and it's going to have as many branches plus 1 as the number of constants that appear on the branch already. So suppose that you've already got m, so suppose m constants appear on the branch already. So what you're going to have a branching rule where on the left-hand side you put in the first constant, for x. And then you'll put in, the next one you'll put in the second constant for x, and so on. So you're going to have as many, so again, this is branching, right? You're going to have as many branches as you have constants that appear on the branch already. So you're going to have n plus 1 new branches. N plus 1 new branches. So you're going to have, and so finally, over on your last branch, you're going to put in a new, where n is new to the branch. So you're going to have one branch for each of the constants that already appears, a, b, c, d, e, f, g, da, 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 m, and then finally in the rightmost branch, when you branch, when you apply existential decomposition 2, you're going to put in, basically you're going to put in the instance that you would have put in back in with the traditional existential decomposition. Okay, so let me give you an example just to make sure that this is kind of clear. So suppose that, let's look back at the tree that we did where when we violated the restriction on existential decomposition, it didn't get us into any kind of trouble, okay? So here were our set members. And so first I'm going to apply, I'm going to now adopt existential decomposition instead of I'm going to adopt existential decomposition 2 in lieu of traditional existential decomposition. Well, in the first case, it's going to look just like existential decomposition. So first I'm going to decompose line number 1, and I'm going to get that from 1. I'm going to call it ED2 because there was no constant, so, that's going to be an A, sorry. I'm introducing a new constant. And now I'm going to apply ED2 to line number 2. So there's one constant that appears on the branch already. So there's going to be 2 branches here. So what's going to happen when I apply existential decomposition 2 is over here, I'm going to have, so this is the instance where of line number 2, where I'm violating the traditional existential decomposition because I'm using the same name, right? And then over here, I'm going to, so this is the instance that I would have gotten where, so B is new, right? So in this case, I'm not violating. This is the instance that I would get when I don't violate the restriction on traditional existential decomposition. So I get that from 2 by ED2. So it turns out in this case, not at all surprisingly, because we just looked at this example already, it turns out in this case that we're going to get 2 different interpretations. Both of these are open. This branch is open and that branch is open. So from the left-hand branch, we're going to get the interpretation where we have one thing in it and we put it into both F and we put it into G. Put it into G. So we're getting this interpretation that we got when we violated the traditional existential decomposition. And then over here, from this branch, we're going to get what the interpretation that we got when we didn't violate the restriction on existential decomposition, where we have 2 things in the universe, and we put one of them into F and the other one into G. So, okay, so that's one idea. Going back to the example that we gave initially that shows why we do have, that illustrates the issues that arise if we do violate or that can arise when we do violate the restriction on existential decomposition. Let's do that tree again using ED2 rather than the traditional existential decomposition. We're going to end up with, okay, so we've got, there's something that's F, there's something that's not F, those were our set members, and if we apply existential decomposition 2, well, first we're just going to decompose line number 1, so we get good old FA, and we get that from. And now when we apply existential decomposition 2 to line number 2, on the left-hand side, we're going to use the constant that already appears, so we have not FA. And on the right-hand side, we're going to introduce the new constant. So here we violated the restriction, and over here we don't violate. And this does not violate the restriction on existential decomposition, the traditional one. So we get this from 2 by ED2. Okay, so let's look at the branch where we've actually violated the traditional the restriction on traditional existential decomposition, and that closes. Okay, fine, but this one is open, and this is the one you would have gotten. So you're going to end up, when you apply ED2 in lieu of existential decomposition, the traditional one, you're still going to end up with the tree that you would have, or in one branch, you're going to end up with the tree or the model that you would have gotten if you had not violated existential decomposition, which is what we've got, where are we? Here, right? Yeah, here. Okay, so this tells us that we have two things, and we put, oops, we have two things, and we put one of them, oh, I see what I did. Not, it should be a not. We put one of them into F, and we left one of them out of F. Sorry, I left out a negation sign when I did this. I'm sure that you guys noticed it, and if we were in a classroom, somebody would have said, you left out a negation sign. When I apply existential decomposition 2 to line number 2, I get not FA, not FB, right? So this is the interpretation I get from that is just what you would expect, that I put one thing into the extension of F and I leave out the other thing. So there's something that's F and there's something that's not F. Okay, so that's the rule. How does this help us deal with the issue that we observed with this? The issue being that traditional existential decomposition traditional existential decomposition with this restriction that we have to introduce a new name leads us to an infinite tree when we deal with this sentence. Despite the fact that we recognize that there are ever so many, an infinite number of finite models for that sentence. We would like to have a tree that gives us those finite models. Okay, so let's go back to that example. So on line number 1, I'm going to have, for all x, there exists a y, lxy. I think this is kind of cool. And so the first thing we're going to do is apply universal. So everything else is the same in the systematic trees, but first we're going to apply universal decomposition, and we end up with, there exists a y, lay, and we get that from 1 by universal decomposition. And now I'm going to apply existential decomposition 2 to line number 2. It's going to branch, it's going to be 2 branches because there's only one constant that appears, right? There's going to be one more branch than there are constants on the branch already. So on line number 3, over here I'm going to have LAA, this is the one that violates, right? So on the left I'm violating the restriction on good old the old-fashioned existential decomposition. And on the right, I'm introducing the new name. So this is what we would have, oh, it's not L, not F, L. This is, on the right-hand side, is what we got when we did the tree with traditional existential decomposition, right? And on the left-hand side, we get the one that we're unable to get when we apply the existential the traditional existential decomposition. So I get that from 2 by existential decomposition 2. Okay, so now, so let's go back. So the first line says everything bears L to at least one thing. Line number 2 says, okay, A bears L to something. And then on line number 3, we have this possibility. Well, maybe A bears L to himself, or maybe A bears L to B. And if both of these branches close, then we know that neither one of the interpretations will work. But if either branch is completed and open, then we have a finite open tree, right? So this branch here is actually a completed open branch, right? We have decomposed the universal quantifier using each of the constants that appear so far, and we've applied existential decomposition to line number 2. And so this gets us that world, right, where we've got one thing that bears L to itself, or, to put it, we've got the universe of discourse has one thing in it, and into the extension of L, we put the ordered pair 1, 1. So 1 bears L to itself. So for us, an open tree is going to be one that has either has at least one completed open branch, or it has at least one non-terminating, one infinite branch. And so let's continue this tree and see what happens, right? So this branch is a completed open branch, but this one is not. And so over here, what we're going to do now is, since we've introduced a new name on the right-hand side, constant, we have to go back and reinstantiate for x in line number 1. And we end up with, so now we've introduced B, whoever he is, into our little world on the right. And this says everybody L's somebody. Yep, in particular, B has also got a L somebody, right? So we get that from 1 by universal decomposition, which is, so this is, we're continuing sort of what we had done in the traditional tree, right? And now, when we apply existential decomposition 2 to line number 4, how many branches are there going to be? Well, there are 2 constants already, so there are going to be 3 branches here. On the leftmost branch, we're going to put in A for Y, so we get L, B, A, and then the next branch, we're going to put in B for Y, we have L, B, B. And then in the rightmost branch, we're going to have what we would have on the traditional tree, namely we introduce a new name, so we have L, B, C, where C is a new name, and we get that line from line number 4 by existential decomposition 2. Okay, so what's going on here? Well, this branch here is a completed open branch, right? Because, so this branch is a completed open branch because we have instantiated for the universal quantifier here, for x in the universal quantifier, each of the names that appears on the branch, right? And similarly, this is also a completed open branch, right? So these 2 branches over here are going to give us 2 more finite models. So this one is going to give us the one where we have 2 things in the universe. I'll draw a picture of it first. We have 2 things. B bears it to A, and A bears it to B, or we have a double arrow, right? And so that's going to give us this interpretation where the universe of discourse is 1 and 2, and into L we have 1 and 2 L-ing each other. 1 L's 2 and 2 L's 1. And for this one, we end up with the interpretation where we also have 2 things in the universe. What's the picture here? We have 2 things, and this one tells us that this guy L's himself, and then this guy L's him. So that's going to have, so into the extension of L, we're going to have 1 bears it to 2 and 2 L's himself. So that's a different finite model. So both of these open branches are completed, and they gave us different finite models. This branch over here, however, is still open, right? So on line 6, let me erase this stuff. On line 6, we're going to go back, since we've introduced C into our little world here, we're going to go back and reinstantiate for X with C, right? Because that's the deal. It's not a completed open branch because we have to go back and reinstantiate line number 1 with the new constant that's been introduced. So we're going to have there exists a Y such that C L's Y. There's somebody whom C loves. So here we had everybody loves someone. Let's think about it as people and loves. Everybody loves someone. Well, maybe A loves himself. Yeah, we've introduced A. A loves someone. Maybe it's himself. Maybe it's a new guy. And now we have to say, well, B loves someone. Well, maybe he loves that guy A. Or maybe he loves himself. Or perhaps he loves the new guy. Now we've introduced the new guy, so we have to say, well, the new guy loves somebody. We get that from 1 by universal decomposition. And now we're going to apply existential decomposition 2 to line number 6. So how many possibilities are there? There are 3 existing constants. So there are going to be 4 branches, right? There's going to be 1, 2, 3, 4. One possibility on line number 7 is that who does C love? Well, maybe he loves A, or possibly he loves B, or yet again, he could love himself. Those are the possibilities. Or he could love the new guy D that we're introducing into our world, and we get that from 6 by existential decomposition 2. Well, once again, let's think about what's going on with these branches. So this is a completed open branch because we've decomposed line number 1 using each of the constants that appears on that branch. And so this is going to give us a finite model. It's going to tell us, here are the literals on that branch. So this branch is there, right? Fancy, right? And so the literals on this branch are these, the things that I've circled in blue. So we have, what does that suggest? We have 3 things in our world, and this tells us that A L's B, say this is A, B, and C. A L's B, B L's C, and C L's A. So it gives us the Elling go-round, as I call it, right? And so that's going to be a universe of discourse with 3 things in it. And we have 1 L's 2, 2 L's 3, and then 3 L's 1, right? That's this one. This, the next one over, the constants on that branch are this. I mean, not the constants, the literals on that branch are these. And so that gives us, and that's also a completed open branch, and that tells us that A L's B, B L's C, and C L's B back, right? In other words, we have a universe of discourse with 3 things in it, 1, 2, 3, and we have into L, we put, we have 1 bears it to 2, 2 bears it to 3, and then 3 bears it back to 2. So that's that one. And then this one, let's do it in a different color. In this branch, the constants are, right, so this is open as well. The constants are these. And so that basically gives us a world, again, with three things in it, where this guy L's that guy, this guy L's that guy, and this guy L's himself, right? And so that's going to give you the, do I have space over here? I don't know. I have, again, the universe of discourse has 1, 2, and 3. And into L, we have, I don't really have space, do I? Let me see. We have, into L, we have 1 L's 2, 2 L's 3, and 3 is a self-L-er, right? So we get that from this open branch. And now, over here, this branch is still open and not completed. So what we would have to do, I'm not going to do it because I'm not going to do this. I promised it was going to be a relatively short recording. I'm not going to make it, it could be an infinitely long recording, but I would expire before we finished. This one, we have to go back and reinstantiate line number 1 using D for X, and then when we end up with an X, we introduce this new guy D, he's got to love somebody, and so when we consider whom he might love, when we apply existential decomposition to, he could love A, he could love B, he could love C, he could love himself, or he could love the new guy E that we introduced. So we're going to have 5 branches when we apply existential decomposition on what would be line number 9. So this goes on forever. So what you end up with is this tree where, you know, over on the left, you are collecting, let's see if this works. You're collecting all these finite models, right? And then, but on the right, this is the one that's going to go on forever and ever and ever. You're going to end up with an infinite. The rightmost branch is going to be an infinite branch, whereas on the left, you're going to end up with lots and lots of models, an infinite number of models. So it's going to end up, so whenever I think about this, what this tree looks like for, you know, you visual people, I have a hard time visualizing this, but what I know is that it's going to be infinitely wide, right? Because this just keeps going and going and going, right? And it's also going to be infinitely long because the rightmost branch is going to go on forever. So for those of you who like to think about shapes, maybe you can think about what shape this tree is going to take. But this is really cool because, you know, it's very clear why we do have this, the restriction on existential decomposition, right? We don't want this to happen. But you know, it doesn't always get us into trouble when we violate the restriction. And so capitalizing on that enables us to come up with this new rule that helps us, that gives us not every single one, but an infinite number of finite models when finite models exist. But you'll also get that infinite one because that rightmost branch is going to continue to be infinite. That's the one that's going to go on forever and ever and ever and ever and ever and ever. My pen's not working, unfortunately. Okay, so that's kind of cool. I thought I would mention that. You know, if things were different, maybe I would give you some exercises to do where you actually apply this rule. Maybe you guys who want to will go back and take a look at the section in the book and play around with it a little bit. But I just felt like it would be unfair if I didn't tell you about it because it's a pretty cool thing. Okay, so that's it for now. So I'm going to